So actually today I'm a bit unprepared again, and Gorinov will be late, or probably he cannot come today. I don't know. He have some big problems, really. And today отработать?
Да, должно.
Okay. So I will speak about some topics of talks that you can take. Actually, you can, I think, tell us that you want to speak about something. We only ask you that your subject is related with symplectic, geometry, topology, or something like that. Okay, so topics. First topic is continuation of construction of Floer homology. After Solomon or something else. It's a big subject. You can speak about that half a year, really. But you can prepare just one topic. Okay, so it's first idea. Second idea. Do you know what is the non-squeezing theorem?
I heard once, but I think about.
Yeah. Okay. Non-squeezing. I don't know how it is written. Theorem. It's Gorinov result. The result, so symplectic topology is based on 2 points. One point is Arnold conjecture, really, and second point is this theory. But it's very good theory. Okay, so I am speaking about statement. So we have space R 2n plus 2 with standard symplectic form. Okay. And in this space I consider the product of two-dimensional symplectic disk of radii r and r to n. It's infinite it's a set of infinite volume, of course. The picture is like that. Infinite volume. And we consider a disk of dimension 2n plus 2 of Rayleigh, probably is better big R, and here small r. Then theorem, Gorinov theorem, that one can symplectically embed this to this if and only if R is at least R. R small is at least R big. So this set is a set of finite volume, and symplectic embeddings, of course, preserve volume, but it's impossible to embed big ball inside a small cylinder. The theorem and one of the proof, there are many proofs now, and at least one of them is based on Floer homology, or like that. So I suggest at least to think about it, or or it's good idea. It's interesting subject. Okay. Next. So generating functions and Arnold conjecture. Yeah, probably. So consider standard example of symplectic manifold. T star of another manifold, say M. I claim that, so I will explain you, probably you know the construction, how to construct many Lagrangian manifolds in that space. One example is the graph of differential of a function on M. For any smooth function, we can consider graph of df. It's, by definition, it's the set of all pairs. I claim, and that is simple, really simple exercise, that this manifold is Lagrangian in cotangent bundle. And this function f small is called generating function. by definition. But now I will explain generalization of that construction. Generalization of generating function, generating family. Generator family. So suppose and we fix some additional manifold W. And consider generic function on the product m times w. On the product. I ask that function big F is generic. I don't explain what is it, but I need it, really. You will see it in a second. Okay, so if we have any smooth function, then okay, I will denote this graph by df. So we have a manifold df big in the cotangent bundle to product by definition. It's Lagrangian manifold in big space. That is big space, big cotangent space. But we want to construct Lagrangian manifold here in that space, in small space. So that is big space and that is small space. So this construction of df small is exactly the construction when w is a point. Okay, what should I do? I take this guy and so let me introduce local coordinates. We have space M. We have coordinate Q on M. We have space W. We have coordinate W small on W big. And we have covector component. P is and say I need a letter Z. So I take this guy. What is that? df is by definition is the set of all Q, W, P, and Z such that P is equal to derivative in the in direction Q of and Z equals to derivative in direction W by definition of df. Now I want to take intersection with subset where Z is equal to 0. That is a subset in that guy. Okay? And I take intersection of df with that guy. So, what is Z, by the way? Z equal to 0. By definition, it is a product of T star M by W. We cancel all covector components. So we have that subset inside this set. And I want that intersection is transversal. It's almost exactly the genericity condition on F big. F should be generic. Transverse. Now I take that intersection. By the way, what is the dimension of that intersection? An exercise. Find the dimension of that guy. Okay, so let M has the dimension N and W. Okay, M. Small. Find the dimension of that guy. That guy is given by that simple formulas.
It should be M plus N.
The dimension of that guy is exactly N plus M. The dimension of that guy. Why?
We want the intersection.
But now we want intersection. So the dimension of that guy is n plus m. Exactly. Of course, it's Lagrangian manifold in big space. So its dimension a half of the dimension of big space. But we can see it explicitly. We have and now find the dimension. What is the dimension of z equal to 0?
It's M.
What?
M?
M?
No.
No.
n minus 1.
What?
N minus 1?
M minus 1?
Yeah.
No. No. So we have the whole space. It's the space of dimension 2n plus 2m. It's the dimension of the whole space. What is the dimension of z is equal to 0? What is the dimension of z?
It's M. And the dimension of z equal to 0 should be something like 2n plus m.
Exactly. 2n plus m. And here is the dimension is n plus m. And what is the dimension of their intersection? How to find dimension of intersection? That guy with that guy. We suppose that intersection is transversal.
It is,
Of course.
it will be n,
What?
n, the dimension of the
Small n. Exactly. So the dimension is exactly n. And I claim that the projection, we have a projection from that space to tangent bundle. And I claim that projection of that intersection to cotangent bundle is Lagrangian immersion. It's an exercise again. How to prove that idea? So no, I can't say the idea. But it's simple exercise. Okay, so what is how to write down the formula for the projection of that intersection to small cotangent bundle? Is the set L F is the set of all pairs where Q in M and P in cotangent bundle and at point Q, such that exist W in W such that okay, W0 check that definition, that it is exactly what I have said geometrically. Now I write down the formula. That is the definition of the projection of that guy to small cotangent bundle. And check that if W, big W, is a point, then we get exactly that LF so we get exactly the definition of generating function. Generating function, by the way, it seems to me that they was known and used like 200 years ago, or like that, functions. But families, it is like 60 years ago. It seems to me. Probably I'm wrong. So that is the definition of generating family. Yes, and F is called generating family for that manifold, that Lagrangian manifold. Probably we need to calculate simple exercise. Simple example. Okay, so I erase all that part. And we consider an example. So in my first example, M is R and W is also R. And function F is equal to what? Function is like that. I ask you, you to draw a picture of LF in T star M in PQ. So I forget that P is equal to dF over dq of q w0. I forget this. Ну что, идите к доске, не бойтесь.
То есть ты немного запутался в этих координатах.
Ничего страшного, сейчас размутаемся.
So yeah, so
Определение есть. Все-таки. Прямо вот.
I don't understand how the function is defined. So this these are the coordinates in W,
Exactly.
and these are in
Yeah.
okay.
Из N.
Okay.
Yeah.
So yes, I want to compute this LF.
First of all, I suggest you to draw the picture of that set.
So this
No, of that set. All pairs such that the function have critical point along the one multiple.
So let's calculate the derivative, and this is something like this. We want this to be equal to 0.
To zero, exactly.
And at the points of 0, at one such point, and then
Where is draw your axis? One Q.
So this is Q, and this is
Exactly.
Q. And so we have that W is equal to 3 square root and plus minus. So let's say it's 1, and this thing is equal to
Ну, знаете, что лучше без корня обойтись, а просто сказать, что это график U равно 3
ну да,
в квадрат,
Ну да.
парабола,
Да.
только повернутая.
да, сейчас что-то не сообразил. Ну, в общем, как-то так.
Okay. But now we want to draw that guy. This.
And so, yes, okay. So let's just see what is the derivative. So
Now we should draw picture in the space with coordinates Q and P.
Yes, but I'm just
finally.
just confused about how I would do it.
Yeah. One equation is that Q is equal to 3W squared, right? And second equation, that is P. P equal to what?
minus W.
Minus W. You should draw such a curve.
Let's see, as we change W. Then it kind of looks the same.
Exactly.
Just go in that direction.
It's a parabola, and of course, parabola is Lagrangian in the plane. It's trivial here, but we see that example is good because it is not a graph of generating function. We have two p for positive q and 0 p for negative. Okay, thank you. So that is really the first and good example, really good example of non-trivial generating family. And I take minus because I wanted to be on the right side. If I take plus, that we will have the same picture reflected under the vertical axis. Okay, so and now I will state theory. Some other, yeah, probably Gorinov also. So suppose that we consider a space T star M again, where M is closed manifold, compact without boundary. And we take non-autonomous Hamiltonian. Sorry. If we take non-autonomous Hamiltonian, we get non-autonomous flow Hamiltonian flow. And now we consider the image of the zero section. Of that space. It will be some Lagrangian manifold, but not a graph of a function in general, of a graph of df. So it's not defined by one generating function. We interested in the case where t is 1. If t is small enough, then it is a function, of course. It's a graph of a function. And theorem is z. And now I will explain what means quadratic at infinity. I will explain that. So, is given by generating family, say f. Where is f defined? F is defined on a product of m by some vector space of big dimension in general. The dimension probably very big. F is called quadratic at infinity if f is equal to the non-degenerate quadratic form plus the function with compact support. Do you know what is support? It's the closure of all points where the function is non-zero. So this part is non-degenerate quadratic form. Form on that guy. And this is, in some sense, small addition. But interesting. Small but interesting. For example, if the function phi is 0, what do we get? good exercise. Where phi is 0, what do we get? What is that guy? If the generating family is W square, sum of W squares plus minus is Q. Надо сделать упражнение. Вот определение опять. Но это еще проще, чем то, что вы делаете. Серьезно. Где производная обращается в ноль? По всем W. W1, W2, W... Сколько там? N большой. Я его даже не пишу. Не интересно. Только в нуле. Какая там, производная? Нулевая. Значит, что это получается? Это нулевое сечение. В точности. Zero section for that example. Simplest example is very good in some sense. So, and how it is connected to the Arnold conjecture? I need to erase some. Okay. So consider an intersection of that Lagrangian manifold with initial zero section. What is that? I claim that it equals to the set of critical points of generating family FB. Why? Because it is exactly the points where P is equal to 0. But derivative along Q is automatically 0. And now we have second condition that derivative along P is equal to 0. It is exactly the condition on critical point. And now, statement which is a theorem, but also it is good exercise, and the theorem, by the way, belongs to Conley and Sander probably. Theorem, it claims that if f is quadratic at infinity, then n generic. then the number of its critical points of F is at least the sum of beta numbers of M. So that is the Conley-Sender theorem, but also it is just a relatively simple exercise. And actually they proved that only for torus of big dimension. But the proof works for any M. So, the corollary that generically image of zero section will intercept initial zero section in big number of points. Много точек пересечения. И это родственная гипотезе Арнольда утверждения. Так. So, and I suggest to speak about that theory. Я тут объясняю, что вы можете делать. Было предложено две темы, да? Первая тема была продолжать построение гомологии Флоера по Соломону. Что угодно сказать, но что хотите, прочесть, собраться, сделать какой-то доклад. Вторая тема была non-squeezing theory. Знаете такую теорему?
Нет.
Тогда я вам сейчас скажу. Эта теорема такая простая теорема, то есть простая не теорема, а утверждение. Утверждение такое, что если у нас есть пространство R 2n плюс 2, стандартное, симплектическое, и в нем мы рассматриваем произведение двумерного диска на R 2n, а диск радиуса R большой. Такой бесконечный цилиндр. Бесконечный, огромный, бесконечного объема. И рассматриваем еще отдельно шар полной размерности радиуса R. Какой-то шар, он может быть очень толстым, он объем конечного. Умеете считать объем шара? Умеете?
Должно считаться.
Ну, должно считаться, интегралом какой-то брать. Зависит от n, я не знаю. Ну, хороший вопрос, кстати. Как посчитать объем шара? Ну вот, тогда утверждается, что вот этот шар можно запихнуть в тот цилиндр симплектически, сохраняя симплектическую структуру, если, только если выполняется неравенство. Вот так вот. Естественно. R большое должно быть больше равно, чем R малое. Потому я их не назвал так, как-нибудь иначе. И это теорема Громова. Хорошая теорема и неожиданная. Ну, то есть, как-то. Потому что естественное препятствие – это объем, конечно, самое первое. Объем мешает. Ну, мешает объем, потому что объем же сохраняется при техническом преобразовании. Ну вот, by the way, I want to add something, and also it's good topic of theory. Good topic of talk. Okay. Hamill's theorem. We again consider symplectic space, standard symplectic space R in power 2n plus 2. Standard space. With coordinates, with standard coordinates 1 e n plus 1 and q1 q n plus 1, and form is the sum of pi of dpi dqi. We consider Z space, and we consider a hyperplane in that space. Hyperplane, let it given by condition, I don't know, say q1 is equal to 0. And now we consider a round hole in it of the size, again, r big. Round hole. And we consider again ball of radii r. The ball will be in 1/2 of the space. Then theorem that we can take the ball and consider some flow, Hamiltonian flow, such that it starts with that ball and finishes with the ball on other side. If and only if, again, R So we can squeeze ball only if it is small. Big ball we cannot squeeze through small hole. It's Camel theorem. I don't remember who is author. Probably Viterbo. Okay. And now we make a break. You can eat. And after the break, I will speak like 15 minutes.
Может, тогда имеет смысл перерыв сейчас не делать, закончить и...
Может быть, Горинов делать. Вот в чем дело.
Хорошо,
Вот в чем дело. Нет, тут... Так бы я, конечно, я бы с вами бы точно согласился. function. Fifth idea was by you, Pushkar, Floer Homology. Of course, I can try to explain it very briefly. What is that? You know what is that?
No, I know the Kigar.
Kigar. Okay, suppose that we have a Riemannian surface of genus, I don't know, G. And suppose that we have Kigar decomposition of three-dimensional manifold such that it is a glue of two copies of bodies with the boundary Z surface. So then people say that we have on that surface a collection of circles, G circles. They cause, how they cause? A circles. Ну, одни там А цикл, вторые Б цикл. A circles. A1, A2, etc. AG. One collection. And second collection is B circles. B1, B2, B1, B2, etc. B, G. And in some sense, it's dual. It's not dual, but I don't remember exactly the conditions. They intersect, they form additional to base.
They should form a basis in first homology, probably.
Probably.
But
A1, A2, etc., B1, etc., Bj is a basis in homologies, for example, but it's not sufficient. There are some additional. Don't remember, just don't remember. But if we consider now we consider G's symmetric power of Z surface. G is here, its index. So what is that? What is that? Is как набор по-английски?
collection.
It's the collection of G tuple of points on SJ. But probably some points they can coincide. Then the guy is manifold by как называется теорема? Не Ньютона, а чьим многочлен? Виета все. Of dimension equal to J. And in some sense it's complex manifold, and in some sense it's symplectic manifold. And we can consider in that manifold a product of A1 times AN is torus of dimension AJ. It's torus of dimension J. One torus and second torus. Second torus. KA, KTB. And of course, one can take symplectic structure such that this torus and that torus, they are Lagrangian torus. So the first guy is symplectic. Second, Lagrangian. And we have two Lagrangian manifolds. If we have two Lagrangian manifold, we can try to construct Floer's theory for that. Homology groups such that their basis is very simple. It's on its intersections of one torus and second torus, and it's easy to find by picture. But the differential is hard enough, and they claim that this homology group are invariant of three-dimensional manifold. We start from Hugard decomposition of three-dimensional manifold, and we construct from that the corresponding Floer homology. And they claim that these homology groups have to prove all conjectures about three-dimensional manifold. They are interesting. They can help in all problem, by the way, and it's wonderful. And also there were a version of Floer homology groups of knots, because knots are connected with three-dimensional manifolds somehow. So that is the fifth idea of talk. And the last, my last, I suggest the following topic. It's interesting, and I will say few words. So it's called want to speak about this. Few words. By the way, it's the name of given type paper. It's also, it was long time ago, say in 91 or 90 when it was published, but it is still very interesting, I think. Okay, so I want to just to explain very short piece of that paper. So, first of all, if we have compact manifold, closed manifold without boundary, then number of its of critical points of generic function is at least the sum of weight numbers. More serious. Okay, I will explain you why this statement is just calculation of intersection index of a curve with hypersurface in some space. Interpretation of that inequality. Okay, now give me a second. So, first of all, what I want to construct an infinitely dimensional space, say N. Infinitely dimensional space. In that space, I will construct a hypersurface. And I will construct, it will be a hypersurface with singularities. The picture is like that. All space is N, and here is sigma. Singular hypersurface. This hypersurface is called, how is called? Swallowtail. Last cost. And after that, I will construct co-orientation. Such that the intersection index is well defined. Of course, with sigma. and I will calculate just one intersection index, C. Мы в цирке, я фокусник. So n is the space of all functions on M, C infinity functions. It is just infinitely dimensional vector space. Very simple manifold. Second, what is really interesting is sigma. Sigma is, by definition, is the set of all functions such that 0 is critical value. I claim that it is a hypersurface with singularities. And it is looking like a swallow tail. It's a good example, by the way. When we get the picture, it seems to me that we should take the space of functions without x cubed and consider exactly that hypersurface, and we get exactly swallow tail. Okay. Now the last idea, how to construct co-orientation. Co-orientation, we again, like it was on the last lecture, we will define only in smooth point. What are, by the way, is question, what are smooth point of sigma? Guess. Try to guess. It should be simple. Какие точки у сигма гладкие?
Такие, что критическое значение достигается с кратностью 2 в одной критической точке.
Кратностью 1 в одной критической точке, и эта точка морсовская. Вот эти точки гладкие, а остальные на самом деле все не гладкие. Там, где или точка вырождена, или их несколько штук. Да. Спрашивается, какая же коориентация? Коориентация такая. Давайте я определю функцию в дополнение к сигме. Дополнение к сигме. I define a potential. So I take difference of n without sigma. So it consists exactly of functions where 0 is regular level, such that f, the preimage of 0 is submanifold, is regular hypersurface. Yes, by definition. I consider the set, I don't know, say f, that's it. It's a manifold with boundary. Yes? Its boundary is f is equal to 0. Boundary, it could be empty, of course. And I consider that space and I calculate its sum of base numbers. Okay? Its function is good function. It's good function. The value of that function is non-negative integer. All these guys are non-negative integers, and we sum up them. And now we say that intersection is in positive direction if this function grows by 1, and in negative direction if this function decreases by 1. Now consider with Morse function f the path f plus t. T is constant from minus infinity to plus infinity. Big path from minus infinity to plus infinity. My question, how many times it will intersect this discriminant sigma? Such a path plus c plus t. How many times it will intersect discriminant? In regular point, this function decrease or increase only by 1. It's exactly Morse lemma that we glue a cell, one cell. If we glue one cell to space, then its homology groups either they increase by 1 or decrease by 1. So, if t is very negative, then the set, какое-то множество, empty, оно пустое. А когда t очень большое, то чему это равно? point, starting point, F plus T is empty, where T is negative, very negative. And if T is very positive, then that is the whole M. So the intersection index with that path is exactly the sum of Betti numbers. So we will intersect the hypersurface at least that time. It's the proof of that statement. And the given type paper is a generalization of that approach to the work of Legendrian submanifolds, really, of that picture. He take another space, another discriminant, but close to that, and prove some close theorems. That is it for today. I will send this paper to channel because it's hard to find it, by the way, unfortunately. Окей. Всем спасибо. I don't know when we will meet. Probably Gorinov will send a letter, email. But really, so Matfak is in some sense is closed on the next week, I think. Okay.